Hi grade 12s. Today we're going to go through weak acids and bases. So we used strong acids and bases before using KW. Now we're going to talk about weak acids and bases and the concept of Ka and Kb. So yet more Ks for you to add to your list. This is lesson 5.6. Okay, so weak acids. Now we know that weak acids do not ionize completely, so we know that by definition here. So for example, hydrofluoric acid will dissociate right into H plus and F minus, but it's not 100%, so I'm going to use equilibrium arrows for that. So it does not ionize completely, and we don't know the percentage here. We'd have to look that up, or you would experimentally determine that, but we don't know how much that is. And we do know that it's not 100% though. So weak bases are the same. They also do not ionize completely. Now weak bases also do not contain the hydroxide ion. Okay, and so they've got a weak attraction for protons. The one that we pretty much usually talk about here is our NH3. So we have NH3 plus water, and we're going to use double arrows, and this is NH4 plus OH minus. Okay, so this is the dissociation here, so that NH3, the ammonium, will steal one of the protons from the water, and that's where we get our OH minus from. So this is why we define NH3 as a base here. Now, we've got something called the acid ionization constant. So this is Ka. So this is just an equilibrium constant for an acid. So for example here, Ka, so whenever we have the Ks, it's always products over reactants. And so for this particular one then, we're going to have H3O plus, and we would square it if we had to, right? Multiplied by, actually we won't for any of these, sorry, none of them will be squared because it's always one proton at a time. C2H3O2 minus, this is acetic acid here, and then divided by, now for the reactants, you are not going to include water because water is a constant, right? So you're just going to have the acetic acid here, the HC2H3O2. So this would be defined as the Ka for this particular reaction, and we're going to use this formula to solve for different variables as we work through some examples here. Now the base ionization constant, so it's exactly the same thing, except instead of calling it Ka, we're going to call it a Kb. And so for this one, again, Kb, products over reactants. So, oh geez, oh shoot. Okay, so products over reactants. Hold on, sorry guys. Just give me a second. Okay, so products over reactants, so it's going to be NH4 positive times the hydroxide ion concentration, and then are you going to include, there we go. Are you going to include the water here? No, you're not. Sorry, my 9s are ready to quiz, and I'm getting like bombarded with messages. Okay, anyways. Focused again. NH3 then. So you're not going to include the water because it's constant. So you're going to have this ratio here of products to reactants set up. And again, don't include the water there. Okay, so Ka and Kb here. Now, the Ka for a weak acid is 2.8 times 10 to the negative 6. Find the pH of a 3.5 molar solution. So this is the kind of question you're going to be getting here. So it gives you the Ka, and it's asking you to find the pH. Now, in order to find the pH is going to be equal to the negative log of the H3O plus concentration, right? So we know that. You guys already, you've done that. You've gone a quiz on that. You're ready to go on it. So this is just a generic acid, so I've just called it HA here. There's no A on the periodic table. So looking at this, you know that you've got 3.5 molar. Now, if this was a strong acid, it would dissociate 100%. And that would mean that this was also 3.5 molar, and you'd just be able to figure out your pH from that. But it is not a strong acid, so that is not true. We don't know what it is. So we're going to set up an ice table. So you're not done with ice tables. So 3.5, initially you've got 0 there. You're going to have a change of plus X here. So you're going to have a certain amount of H3O plus and A minus here. And this is going to change by negative X. So this is going to be 3.5 minus X. Now, we're going to set up our Ka equation here. So Ka, again, products over reactants. So H3O plus multiplied by A minus, all divided by the concentration of HA. Now, if I subbed in my values here, that 3.5 minus X would end up being a problem for me, and I'd have to use the quadratic equation, and I don't want to do that. That takes a long time. So looking at this, though, we can see that 2.8 times 10 to the negative 6 is quite a small number, okay? So because it's so small, we can assume that X is small, okay? So we can assume X is small. Okay, so because the Ka is small, we can assume that X is small, because what that would mean that HA is a lot bigger, so HA is going to be a lot bigger than the reactants, making that number very small. So that tells us that X has to be small. So if we do that, that's going to help us out mathematically quite a bit here. So now you know that the Ka is 2.8 times 10 to the negative 6. And I'm just going to sub in my values here, divided by, and this is going to be 3.50. So you end up with getting X squared there, so you're just going to do the algebra on that. I'm going to skip this because you guys know how to do that. You're going to solve for X, and when you do that, X is going to be equal to 3.1 times 10 to the negative 3. Now, X is going to be equal to the concentration of H3O plus. So now you're going to dump that into your pH equation here. So I'm just going to recopy it. pH is going to be equal to the negative log of the H3O plus concentration. So it's equal to the negative log of 3.1 times 10 to the negative 3. And once you work that out, you end up with an answer of 2.50. Now remember, you've got 2 sig figs coming from your Ka here, so you need 2 decimals in your answer here for the pH. Okay, so that will be your answer for this particular question. All right, next question here. So calculate the concentration of all species in a 0.25 molar solution of the carbonic acid here. Now, looking at this, you are going to need, I think it's on a violet piece of paper, and it's called a Ka table, and it should have at the top relative strengths of acids. So everyone find that table right now. So relative strengths of acids, and it's got the acid, reaction, and the Ka listed there for each of them. Now, this question did not give you what the Ka value is, but you can look it up on this chart, okay? So you'll notice that the first 6 just say very large, and that's because those are strong acids. So we're just going to assume that they dissociate at 100%. If it has a Ka value associated with it, then it is known as a weak acid. Okay, so let's work through this problem here. You know that you've got 0.25 molar here, so let's do our ice table, and then we're going to change it by an X, 0.25 minus X, and again you are going to assume X is small because the Ka is small. So let's look up our Ka first of all. Forgot to do that. So if we find it on here on your chart, if you look up carbonic acid, you're going to look for it in the left-hand side of the reaction, okay? So you find the carbonic acid on the left-hand side, and it's on, it's number 4.4 times 10 to the negative 7. Okay, so 4.4 times 10 to the negative 7. So I get that from the chart. Now, because that's a small number, I can assume x is small. And again, you have to write that down, that assume x is small. It's going to be important in your problem solving here. Just you always have to show, right? You have to identify and show how you're doing things. Okay, so Ka then is going to be equal to H3O plus multiplied by HCO3 minus, and then that's all going to be divided by 0.25. Now, oops, sorry, I'm jumping spot to spot here. Just a minute. And that's going to be, the carbonic acid here, the H2CO3. Now we can sub in our values. So I know that I've got 4.4 times 10 to the negative 7. Now I get that from the chart, okay? So from the Ka table, you're gonna have to use that. And then I'm just gonna sub in what I have here from the ice table. So it's going to be x times x, divided by, and I'm only going to use 0.25. I can drop that minus x because x is small, and that's going to make my math a lot easier here. So I'm just going to work up here. So you're going to go through, you're going to solve for x, and x is going to be equal to 3.3 times 10 to the negative 4. So now I look at the question. The question is asking me to calculate the concentration of all the species in a 0.25 molar solution of H2CO3. So looking at that, I've got different species here. I have to calculate this concentration, this one, and this one. So I've got 3. So H3O plus is going to be equal to HCO3 minus, because they're both X, and that's going to be equal to the 3.3 times 10 to the negative 4. Don't forget the capital M for molar, K, or moles per liter. And now I also have to calculate the concentration for the H2CO3. So H2CO3, for this one, you're going to take 0.25 and you're going to subtract the 3.3 times 10 to the negative 4, and then you're going to get an answer of 0.2497 molar, but you can only have 2 sig figs, so it actually just ends up being 0.25 again, but you should always check that. Okay, so that would be how you would do that question. You would just have to use your Ka table to find it. Let's do another one here. This is for a base, so it's going to work again exactly the same, except we're using a Kb instead of a Ka, but mathematically everything is going to work the same here. So calculate the pH of a 0.1 molar solution of hydrazine, which is a weak base. So Kb equals 1.7 times 10 to the negative 6. So if I look at my formula, I would give you this formula here. So this is one of those ones that is going to steal the proton from the water here. So giving me N2, sorry about that, H5 plus OH minus. Okay, so set up my ice table. Now, let's look here. I have the Kb available to me, which means that I can calculate the concentration of that OH minus, but I'm asked to find the pH. So there's a couple of different ways we can do this. Well, I'll get there. Let's go ahead and start this first. So I've got 0.100. Okay, I'm going to assume x is small. Kb into H5 plus multiplied by OH minus all over into H4. Sub in your values. So 1.7 times 10 to the negative 6. I've got 2 x's all over 0.100. Now, once I do that, I solve for x, and I get x being 4.12 times 10 to the negative 4 molar. But now I'm asked to find the pH. Now, I know that the hydroxide ion concentration is 4.12 times 10 to the negative 4. So there's different ways I can do this. I can use Kw, because remember our Kw formula, which is OH minus multiplied by H plus, and that's always going to be 1 times 10 to the negative 14. So I can use that to solve for H plus. That's a plus there. Or I can go ahead and find the POH and then take 14 minus the POH to get the pH. That's what I'm going to do just because I don't know why. I find I like it better. No good reason though. Either way are completely acceptable. So you can use KW or you can find the POH first. So I'm going to do this. So the POH is going to be equal to the negative log of OH minus. And so you're going to get an answer of 3.385. Okay, so 3.3, you know, I should have said before, I don't think I did. Don't use the KB for the significance. Use the concentration for the significance, which means I think I probably, if I go back, don't think I did that here. Yeah, so I need 3 sig figs here, so I would need another digit here, whatever it is. Add that in if you had it. Sorry about that. Okay, let's go back. There we go. Okay, so I've got 3.385 for my POH, so therefore pH is going to be equal to 14 minus this number, and that then is going to be equal to 10.615. And that would be your final answer, and you've got to have 3 decimal points because of the 3 sig figs there. Okay, so these questions are all multi-step. Now make a note of this. You will come across this in your assignments when you do it. Ka multiplied by Kb is equal to Kw, okay? So Kw, of course, being 1 times 10 to the negative 14. So always keep that in mind. You've got a Ka table there, but notice that you don't have a Kb table. Now, if you look at your Ka table, all the forward reactions are acidic reactions, but if you look at the reverse reaction of all of them, those are the base reactions, right? So this is where we have if we look at the reverse, we could find the Kb for the reverse reaction. So, and you will be asked to do that. And so how you would do this is you would find the Kb by looking at this equation here. So you'd find the Ka, take the Kw divided by the Ka to get the Kb. Anyways, we can talk more about that in class, and if you do your assignments, you will come across that at some point there. Okay, so you can take a look at exercise 28, and I will post the key to that as well. Okay, thanks everyone.